When man leaves Earth for the first manned mission to the moon, his mission is one of exploration. He will be pushed beyond the confines of the atmosphere in his Apollo spacecraft by the Saturn V rocket. The three astronauts will first enter a parking orbit around the Earth. After a thorough checkout of the spacecraft, the Saturn IVB engine will be fired to begin the trajectory that will take them to the moon. The spacecraft will break into orbit around the moon. The lunar landing craft, called the Lunar Module, will be landed on the surface by its two-man crew, leaving one man in the orbiting command module. The landing will represent the first touchdown of man on a celestial body other than Earth. The astronauts must set up an experiments package that will continue to send data to Earth after they have left. They must also collect geological samples of the surface, which they will bring back to Earth. The lunar crew will lift off in the ascent stage of the lunar module, rendezvous and dock with the orbiting command module, and return to Earth, leaving the lunar module in orbit around the moon. A safe landing on the moon has some unique facets due to the lunar environment. First, the gravity field of the moon is only 1/6 that of Earth. Because of this, the velocity required to maintain a lunar orbit is only about 1 mile per second, as compared with more than 5 miles per second required to maintain a spacecraft in orbit around the Earth. Therefore, the lunar module will be traveling much more slowly than an Earth-orbiting vehicle. Second, for practical purposes, the moon has no atmosphere. Therefore, the lunar module needs no heat shield to protect it from the friction-induced atmospheric heating, such as is required for spacecraft landing on Earth. On the other hand, there is no atmosphere to assist in slowing the spacecraft or in landing it on parachutes as on Earth. The lunar module must rely on its descent rocket engine for braking and landing. The landing site is chosen on a portion of the moon well surveyed by previous unmanned and manned missions. It is located so that communications with the lunar module will be maintained during the powered descent maneuvers for landing, lunar surface activities, and later ascent maneuvers. The time for landing will be early in the lunar morning so that the sun will be behind the lunar module and give the best contrast for visibility. Prior to the descent, the command module and lunar module will be in a circular orbit of about 60 nautical miles altitude. With 2 astronauts in the lunar module and 1 in the command module, the 2 vehicles undock, and the command module pilot visually inspects the lunar module. Later, a safe clearance will be established between the 2 vehicles prior to the first descent maneuver. This descent maneuver, called descent orbit insertion, takes place 180 degrees from the beginning of the powered braking and landing sequence for efficiency. It is performed by a retrograde burn of the lunar module descent engine. This places the lunar module in an orbit with an apoloon or high point of 60 nautical miles and a paraloon or low point of 50,000 feet. At the 50,000-foot altitude level, the powered descent begins. What happens from this altitude to touchdown is the primary focus of this film. The firing of the descent engine at 50,000 feet marks the beginning of powered braking. At this time, the velocity is about 5,500 feet per second, or about 3,600 miles per hour, and the range to go to the landing site is about 270 nautical miles. This phase is about 8 minutes in duration and is completed at an altitude of approximately 7,000 feet, about 5 nautical miles from the landing site, with a velocity of about 500 feet per second, or about 340 miles per hour. This marks the beginning of the final approach. Up to this time, the engine has been firing essentially in a horizontal direction, and with the crew unable to see in the forward direction. At the beginning of the final approach, the crew can, for the first time, see the landing site, see where they are going. The transition from powered braking to final approach is called high gate, a term used by aircraft pilots to mark the beginning of their final approach to the airport runway. This phase is designed to give the flight crew maximum visibility of the lunar surface in order to assess the safety of the flight path and the terrain in the general area of the landing site. It is about 2 minutes in duration and terminates at an altitude of about 500 feet, about 2,000 feet from the landing site, with a velocity of about 60 feet per second, or 40 miles per hour. The transition from the final approach to the landing phase is called low gate, again from the aircraft pilot term designating the beginning of the actual landing. The landing phase is designed primarily for ease of manual control takeover by the crew, if necessary, for the final site selection and touchdown on the lunar surface, with 0 horizontal velocity and a touchdown descent rate of about 3 feet per second, or 2 miles per hour. This is analogous to a helicopter landing. Throughout all 3 phases of the lunar descent and landing, the safety of the flight crew is paramount. Their safety and the successful landing are dependent upon the smooth interaction of several lunar module systems. The heart of these systems is the primary guidance, navigation, and control system called PINGs. This consists of 2 subsystems, the primary guidance computer and the inertial measurement unit, or IMU. The computer is the brains of the system, and for purposes of the lunar landing contains 2 subsystems. The guidance and navigation section, which contains the basic logic and targeting supplied by the mission planners to shape the trajectory to satisfy operational objectives and constraints within the system's capability. And the autopilot, corresponding to the automatic pilot found on commercial airliners. At the beginning of powered descent, the computer contains the most accurate possible estimate of the lunar module's position and velocity. This information is sent from the Mission Control Center prior to descent orbit insertion. The inertial measurement unit is the primary sensor, detecting changes in velocity and attitude of the lunar module through internal accelerometers and gyros. It sends this information to the computer. The computer then sends control commands to the descent propulsion system, referred to as DIPS. This is the rocket engine used for the lunar descent, and its controls consisting of a throttle and a gimbal capable of plus or minus 6 degrees of motion. This engine has a maximum thrust of about 10,000 pounds for efficiency during braking, and can be throttled from 6,000 to 1,000 pounds for controlled operations in the final approach and landing phases. The computer's guidance and navigation section controls the throttle, while the autopilot controls the gimbal for slow-rate attitude changes. If higher-rate attitude changes are needed, another system comes into use, the reaction control system. This consists of 4 groups of 4 small control rockets mounted on the lunar module to control pitch, roll, and yaw. The reaction control system is also controlled by the computer's autopilot. As the lunar module gets closer to the surface of the moon, yet another system comes into play, the landing radar, which provides updated direct readings of altitude and velocity as the lunar module approaches the surface of the moon. The landing radar is mounted at the bottom rear of the descent stage. It can be directed to 2 positions, one for braking when the lunar module is nearly horizontal, the other for final approach and landing when it is nearly vertical. The landing radar consists of 4 beams, 1 for determining altitude, 3 for determining relative velocity. Throughout the descent, ultimate control over the systems can be exercised by the crew through the computer display and keyboard called the DISCI. Reviewing the systems quickly then, the primary guidance, navigation, and control system consists of an inertial measurement unit, a velocity and attitude sensing device sending information directly to the computer. The computer sends control commands to the descent propulsion system and the reaction control system. As the lunar module approaches the moon's surface, the landing radar sends direct altitude and velocity updates to the computer. The crew monitors the descent and maintains ultimate systems control through the computer display and keyboard. With this general view of the systems, we are now able to take a close look at the powered descent and landing sequence. As the lunar module approaches the 50,000-foot level for the initiation of powered braking, it is in a face-down attitude to afford the crew a view of the lunar surface for gross navigational checks. Should there be a decision not to fire the descent engine, the lunar module will remain in a safe orbit around the moon of 50,000 feet by 60 nautical miles and will rendezvous with the command module. At 50,000 feet, with the landing site still beyond the horizon, the crew ignites the descent engine. It builds to full thrust, marking the start of the powered braking phase. At this time, the crew has the option to be face up or face down, but must be face up by the 40 to 30,000 foot level. This phase of the trajectory is controlled automatically by the computer with inputs from the inertial measurement unit. When the lunar module reaches the 40,000 to 30,000 foot altitude range, it is rolled onto its back, either by the pilot or automatically. Now the landing radar acquires the surface and begins updating the computer estimate of altitude. The crew can no longer see the moon and is totally dependent on the landing radar and computer displays for knowledge of where they are. At around 20,000 feet, the computer begins throttling down the descent engine to about half thrust to achieve high gate. At about this time, the crew will see the lunar surface for the first time since the roll maneuver. As the lunar module has been descending, it has steadily been pitching up. At high gate, approximately 7,000 feet altitude, it will be within 50 degrees of vertical. Now, for the first time, the crew is able to see the landing site about 5 miles away. There is now the option to stay with the automatic system or to take over manual control. Nominally, he will stay with the automatic system to low gate. The crew uses the landing point designator, a grid on the commander's window, to locate the site. The computer display tells them where the site should be relative to the grid and updates the position every 2 seconds. During this approach phase, about 2 minutes in duration, the crew can manually change the point to which the automatic system is steering. This is called redesignation and is used to avoid hazardous terrain features in the landing area. At about 2,000 feet from the landing site and at an altitude of about 500 feet, the lunar module achieves low gate, the beginning of the landing phase. If the spacecraft commander likes where the automatic system is taking him, he elects to stay with it. If not, say a boulder or crater obstructs the landing site, he can manually alter the lunar module course to a new site. The speeds are now low enough and the trajectory so designed that the crew will normally take over manual control. The velocity should be in the neighborhood of 60 feet per second horizontally and 16 feet per second vertically. The commander is making his final decisions as to the exact location of the landing site. If he stays with the automatic trajectory at an altitude of about 150 feet, the spacecraft has 0 horizontal velocity and is descending at about 3 feet per second. Probes from the landing gear touch the lunar surface, turning on a light in the cabin. The spacecraft commander cuts off the descent engine, and the lunar module touches down on the moon. Reviewing then, preparation for lunar descent begins in circular orbit 60 nautical miles above the moon with the undocking and separation of the command and lunar modules. Descent orbit insertion occurs 180 degrees from the beginning of powered braking with the retrograde firing of the lunar module descent engine. The lunar module coasts down to the 50,000 foot level about 270 miles from the landing site with a velocity of 5,500 feet per second or 3,600 miles per hour. At this time, the descent engine is fired for the powered braking phase of the landing trajectory. The lunar module is in a face-down attitude until it reaches the 40 to 30,000 foot altitude range, then rolls onto its back to give the landing radar surface acquisition. The transition to the next phase, the final approach, is called high gate and occurs at an altitude of approximately 7,000 feet, about 5 nautical miles from the landing site, with a velocity of about 500 feet per second or 340 miles per hour. At high gate, the lunar module, which has been slowly pitching up during the braking phase, is within about 50 degrees of vertical so that the landing site is visible through the forward window. Now, the crew locates the landing site through the landing point designator grid on the window from information provided by the computer display and assesses the conditions at the landing site. About 2 minutes later, at an altitude of about 500 feet, 2,000 feet from the landing site with a velocity of about 60 feet per second, the lunar module will pass through low gate, the transition from the final approach to the landing phase. At 150 feet altitude, the horizontal velocity will be 0 and the descent rate about 3 feet per second. When the landing probes touch the surface, the commander shuts off the descent engine, and the lunar module touches down. While the success of the landing is of obvious importance, the overriding concern is for crew safety at all times. While all other phases of the lunar mission can be demonstrated in Earth or lunar orbit, the manned lunar landing can be demonstrated only by its accomplishment. Should there be a malfunction of any of the systems, the landing could immediately be aborted. Should there be a failure in the primary guidance, navigation, and control system, a backup abort guidance system would take over and enable the lunar module to abort the landing and ascend to orbit for rendezvous with the command module. Should the descent engine fail, the spacecraft commander would hit the abort stage button. This automatically separates the ascent and descent stages, fires the ascent engine, and switches to ascent guidance, taking them back into orbit and a subsequent rendezvous with the command module under control of either the primary or abort guidance system. The importance of the descent and landing phase of the lunar mission is obvious, for it is only upon its successful completion that we will begin manned exploration of the moon.